Stat 1150. Let me tell you what's going on here. What I'm trying to do is I tried to create a study guide that's going to give you problems similar to what you're going to see on your final exam. So what I've done is I've uploaded a study guide for the final exam for practice only. It's going to appear that it impacts your grade. It does not. You don't have to do this. Highly recommended you do it because the questions that I've chosen for the study guide for the final exam are very similar to the ones that, at least very similar to some of the ones you'll see on your final exam. There's still a little bit of a difference. So gang, you'll see that for this particular semester, this was summer 2016, taking their exam, the first attempt on, well, the first option, they only get one attempt, on the 25th from 10 a.m. to 2. I'm giving 15 extra minutes just in case. But anyway, this is going to be available for you to use as practice. So what I want to do is I want to run through this and tell you how I would do these problems. Now, the very first thing I want to do is I want to exit this full screen here and bring up the calculator because we'll be using the calculator from time to time. Okay, so first question, worth 5 points. A survey of eating habits showed that approximately 5% of people in a certain city are vegans. Vegans do not eat meat, poultry, fish, seafood, eggs, or milk. Well, that's no fun. A restaurant in the city expects 400 people on opening night, and the chef is deciding on the menu. Okay, seems reasonable application of statistics, right? Treat the patrons as a simple random sample from the city and the surrounding area, which has a population of about 60,000. If 20 vegan meals are available, what is the approximate probability that there will not be enough vegan meals? That is, the probability that 21 or more vegans will come to the restaurant. Assume the vegans are independent. That's a wordy problem. Well, gang, anyway, this is a proportion problem. So I'd like to write down some information here. So first of all, I know that my P for this problem is 5%. I'll tell you what I want to do. I want to bring this up so you guys can see what I'm writing. Things like today where it's so much easier to do this kind of thing in class, face-to-face, but it's just not where things are going. Okay, so when I read this problem, I see that the description of my population is 5%, so I have 0.05, and it looks like they're expecting 400 people on opening night, and they're wanting that the probability, so we're talking about the probability that X is greater than 21 out of 400. So probability to 21 or more. So actually, technically, it would be this. Okay, so what we would want to do is we want to think about this in terms of what the sampling distribution looks like. So the sampling distribution for our p hat will be equal to p, and the standard error for our p hat is the square root of p times 1 minus p over n. So I know that the mean of the distribution is going to be 0.05 because that's the value that describes the parameter for our population. And then this will be 0.05. 1 minus 0.05, of course, is 0.95. And my sample size appears to be 400 people. So let's put this in our calculator and see what happens with it. So turn it on. So square root of 0.05 times 0.95 divided by 400. So I'm going to go out to 4 places because it just makes my answer better. So 0.0109 will be the standard error. All right, so what I need to do now is I need to put this in my calculator. So I'm going to go into normal CDF, and I want 21 out of 400 up to infinity with a mean of 0.05 and a standard deviation of 0.0109. Okay? So hit enter. My probability, it says to go to 3 places. So that looks like 0.409 to me. So I'm going to type that in very carefully. I'm going to check my answer. And your input is correct. Cool. Knew it would be, but well, I thought it would be. Okay, problem number 2. Use technology to find the indicated area under the standard normal curve. Now, gang, when you see that key word, or I'm sorry, that key phrase right there, standard normal curve, what should you think? Mean 0, standard deviation 1. We're talking about the distribution of z-scores. And z-scores always have, from a normal distribution, z-scores always have a mean 0, standard deviation 1. So the first problem says find the area in the standard normal curve to the left of 0.52. So which graph represents that? Well, guys, in the middle of the distribution, for the standard normal distribution, in the middle we have mean 0. So all the numbers over here are positive and all the numbers over here are negative. So since I'm focusing on 0.52, I know the 0.52 has to be to the right of 0. So, and it's not between 2 values, so it couldn't be A, couldn't be B, it could be C, it could be D. But we went to the left of 0.52, so clearly, guys, C would be the correct graph. Now the area to the left of 0.52, I'm going to use my calculator. And I'm going to use normal CDF. To the left, I'll tell you what, let me get that out of the way. So to the left, I'm going to start out with negative E99 up to 0.52. Mean 0, standard deviation 1. So the answer rounded to what they want. 4 places on this one. So that's going to be 0.6985. Because again, that 4 rounds up to a 5 because that 5th digit is 5 or bigger. So 0.6985. All right, which graph shows the area in the standard normal curve to the right of 0.52? Well, guys, that's clearly going to be part A. And the area in the standard normal curve to the right of 0.52. Well, we can do this one 2 different ways. I could just go 1 minus the answer from the previous problem because I know the area under the curve is equal to 1. So I could get my answer that way, which is by far the easiest, is 0.3015. However, I want to use this not only to get the right answer, but to use it as an opportunity to teach. If I'm going to put this in my calculator point blank, what did I do there? Then I would do 0.52 up to positive infinity, comma 0, comma 1. So if I hit enter there, you see that I get exactly the same answer all the way out to what, 9 or 10 digits. So gang, correct answer 0.3015. All right, so let's check our answer. We know it's going to be right, so good deal. Okay, question number 3. According to a reputable magazine, 32% of people in a certain large country have sleepwalked. Where do they come up with this stuff anyway? Have sleepwalked at least once in their lives. Suppose a random sample of 300 people showed that 75 reported sleepwalking. The null and alternative hypotheses for a test whether the proportion of people who sleepwalk is 0.32. So you have the null and alternative hypotheses given right here, respectively. The conditions are satisfied. That's cool. Look at the technology output. All right, so let's tell you what I'm going to do. I'm going to put this down there. I'm going to make this a little bit larger, and I'm going to move the technology output right there. So this is what you're going to see, something like this if you put this information in your calculator. So the Z statistic, that's just going to be the Z statistic. So to two places is negative 2.60. The p-value is given as we want to go to three places there, so that's 0.009. So the conclusion, since we're testing at 0.05 and our p-value is less than 0.05, we're going to reject the null. So there is sufficient evidence to conclude that the proportion of people who sleepwalk is not 0.32. Check answer. Input is correct. Now, gang, we can use a little bit of kind of common sense here, if you will, statistical common sense, that we can not only conclude that sleepwalk is not 0.32, because from the test of hypothesis, if we reject the null, we're left with the alternative, which says p is not 32. But we can see that our sample proportion from the output is 0.25. So we can actually further, from the confidence interval, conclude that the percentage, or I'm sorry, the proportion who have sleepwalk is less than 0.32 because our sample proportion is less than 0.32. It'd be kind of goofy if we conclude it's bigger than 0.32. Now we can only do that by an additional statistical test, a confidence interval, which isn't part of this question. So again, just doing a little bit of teaching here along the way while I'm working the problems. All right, so the accompanying table gives the distance from a particular city to 7 other cities and gives the time for one randomly chosen commercial plane, commercial airplane to make that flight. Do a complete regression analysis, scatter plot, and so on and so forth. Well, gang, I've got the times here, and I want you to be able to see the calculator. So let's do this. Okay. Now, so I want to enter these values in my calculator. So to do that, I would go to Stat, and I would go to Edit. And first thing I would do is clear out the old numbers to make sure that I don't get an error entering my new numbers. Okay? So 1.169, this is going to take forever. 2.983, 3.389, 1.698, 2.401, 1.793, and 0.278. All right, these other numbers are going to be a little bit easier to enter. 2.89, 6.01, 7.28, 4.39. Don't you wish I would be there at your exam and read the values to you? It's not going to happen. 1.15 and 1.16. I'm glad that's over. That was boring. All right. Now, first of all, we need to make sure that we've got the same number of numbers in L1 and L2. If I've got more numbers in L1 than L2 or vice versa, I'm going to get an error when I do regression analysis. Regression requires us to have 2 measurements on each subject. In this case, the subject is a randomly chosen airplane. So we've got, actually these are cities. So it's got the distance from a particular city to another city, and then it's got the time it took in hours for the plane to make that trip. All right. So first thing I want to do is I want to make a scatter plot and try to compare it with the one that they're given there. So make sure it's on. Make sure the first one is selected, and I have X list and Y list there. Okay. So I'm going to go zoom 9, and I can see that I get, guys, I got some crap in there. So let me go in and go into Y equals. Okay, apparently it's a sophisticated graph there. So let me get rid of all that stuff. So, all right, cool. So which one does it look like? Well, clearly it's either B or D, and I have to look a little closer to see to see which one I get, see which one I need. If I come in on D, I can see that it looks like my biggest is out here at 3.5, and that's biggest at 3.5. It's kind of hard to tell, isn't it? Well, I can see here that my lowest measurement has a Y value about 1. So is that the way that would be? So my lowest measurement, which is 0.278, has a Y value of 1.16. So guys, that's not the case over here in D, so I'm pretty confident that B is the right one. Does it seem that the trend is linear or is a noticeable curve? The linear model is appropriate because there is a linear trend. Okay. Find the equation for predicting time from miles. Guys, I'm going to use my calculator here. There are formulas for that, but this makes it much easier. So I go to linear regression t-test. Make sure I have L1 and L2. And make sure I have Y1 here. Now, I've shown you how to do that in a previous video. But let's, just in case, let's say it's not there. So you're going to go to variables. You're going to go over to Y variables. You're going to go to function. And you're going to hit select for Y1. Now, what that will do when we hit calculate, it will draw the linear regression model on our scatter plot. So let's hit enter. You can see that we're in the form y equals a plus bx, so b is my slope. So I have an a of point, let's see, what's it tell us around to 2 places. So my a here would be 0.77, and my slope is 1.87. All right, interpret the slope. Well, the slope just tells me that as I increase x 1 unit, well, x in this case is the distance from a particular city to another city. So for each additional 1,000 miles, not every additional hour, that's my y value. So the time goes up the slope, which is 1.87. So guys, remember that that slope focuses on an additional change, one additional unit on the x, and it predicts what our change will be on the y. Now the intercept is tells you when the value of x is 0, what is our y value? Well, again, our y value is predicted time, so a trip of 0 miles would be, we'd be needed to focus over here on the time measurement. So guys, we're looking at 0.77 hours. Okay. Use the regression line. How long should it take to fly nonstop 3,000 miles? Well, this is really cool. We have that Y1 in there. You can just hit graph. Now you'll see it has the linear regression model on your scatter plot. So if I go second function trace value and just type in 3,000, it will approximate. Okay, why is that not the case? Oh, guys, these things are given in thousands of miles. So we just need to put a 3 in there instead of 3,000. Alright, so it looks like 6.40. This is round to 2 places. So 2 places looks like to me about 6.40. Alright, a lot going on here. Check the answer. I'm pretty sure we got it correctly because we went through it very slowly. Alright, next problem. A poll reported that 1831 out of a total of 2178 in a particular region said they had a great deal of confidence or quite a lot of confidence in the military. That's good. Assume the conditions for the CLT central limit theorem are met. Find a 95% confidence interval for the proportion. Well, guys, proportion tells you we need a 1 prop z interval. So if I go to stat, go over to test, scroll down to the interval choices, this is a 1 prop z interval type of problem. So my x is the count out of the hole. It has the characteristic that I'm measuring. And then n is the total number of subjects, in this case adults, that were surveyed. Alright, so we want a 99% confidence interval. You can put 99 or 0.99, both work. And we get our confidence interval very, very quickly. Alright, so the left bound, what are we rounding to? 3 places, so 0.820. And the right bound is 0.861. Interpret. So we would say that we are 99% confident that the population proportion of adults having a great deal is between, that every sample proportion, guys, we've talked about this in previous videos, so I'm not going to beat a dead horse here. For reasons I've explained before, our confidence is on what we are estimating. So let me read that again. We are 99% confident that the population proportion of adults having a great deal or quite a lot of confidence in the military between, that's a lot of words, is between those two values. Find an 80%. Well, guys, this is really simple. Once we've got the information in, scroll down to A again. All we need to change here is 80. Hit calculate and we get our answer. Alright, so the 80% left bound is, again, we go 3 places, right? 0.831 all the way up to 0.851. So again, we are 80% confident that the population proportion of adults having a great deal or quite a lot of, okay, so same thing there. So 80%, and it's between 0.831 and 0.851. Now, which interval is wider? Well, which do we have more confidence in? Did I mess that up? No, what's going on here? It says 99% up here, but then, okay, which interval? So the width of the 99% confidence interval is, Oh, okay, so it wants us to find the width. Well, guys, the width is just the big number minus the small number. So this is 0.851. We're looking, we're doing the 99 first, so let's go up here and do that. So 0.861 minus the 0.82. Now, don't confuse this with the margin of error. The margin of error, we take the difference and divide by 2, because the margin of error is the distance from the estimate to the end of the interval. It's not asking about the margin of error. That's a different thing. That's 6 of 1, 12, whatever. This is a different question. So we're just looking at the width of the interval. So in this case, the width would be 0.041. And the width of the 80% is going to be, so the 80 is 0.851. You can probably do this in your head, I can. But I'm teaching, not doing. So it's going to be 0.02. We're going to 3 places, so 0.020. So the 99% is wider. It's got to be wider. We have more confidence that we are capturing the unknown quantity that we're looking for. So how would a 90% interval compare? Well, the 90% interval would be narrower than the 99, but wider than the 80, because as intervals get wider with increasing levels of confidence. So all right, gang, this is going to take a while, isn't it? All right, in a certain state, the recent average critical reading standardized test score was 527. The standard deviation was 50. The scores were normally distributed. What percentage of standardized test takers scored 500 or less? Now, 500 is to the left of the mean. So I'm looking for a score that is left of the mean, and since I'm looking for less than 500, I need something shaded to the left. Well, that can't be it, because that's a bigger number, so it has to be this one right here. So what percentage? To answer this question, what do? Well, guys, we use the normal CDF key. So I need left, which is negative E99. My right bound is 500. My mean is 527. And a standard deviation is 50. So rounded to what? 1 decimal. So they want us to change it to a percentage. So the easiest thing to do there to change to a percentage is multiply by 100. Rounded to 1 place will be 29.5%. All right, what percentage of standardized test takers scored more than 527? Well, guys, think about it. 527 is the mean. Greater than the mean is just going to be finding the value in the middle, and it's going to be everything to the right of it. And gang, the percentage has to be 50%. All right, that was an easy question. Question number 7. College women have heights, mean of 60, standard deviation 1.7, complete A through D. The 75th percentile. All right, gang, what does the 75th percentile tell you? In general, what does percentile tell you? Let me get this up. What does percentile tell us? Percentile tells us for a particular score, the percentile is always the percent below. As rarely in mathematics can you say something is always. Percentile is always below. So gang, for the first one, the 75th percentile, we want to find the score that has 75% of the observation below it. So that's going to be really easy. We use that magical key. Help we turn on the calculator. That inverse norm key. We want 0.75 of a mean of 60. Standard deviation 1.7. So the 75th percentile rounded to 1 decimal place is 61.1. Find the height at the 25th percentile. Well, gang, that's the same thing we had before. In fact, I can just hit second function entry and bring down what I had there and put in the 25th percentile. Rounded to 1 place, that'd be 58.9. Find the IQR. Well, guys, the IQR is just the Q3 minus Q1. So Q3 minus Q1 is going to be 61.1 minus 58.9. So 2.2 would be the IQR. Now, is the IQR larger or smaller? Well, guys, your IQR in this case is going to be larger than the standard deviation. Now, why? Let's take this as an opportunity to learn something. Why is it larger? Well, guys, when we do a graph of a normal distribution, as I tried to teach you previously, we have the mean in the center. And then right at this magic place here, if you know much about calculus, you know that this is an inflection point and it has something to do with concavity. I'm not really going into that. But this is a standard deviation above the mean, and this is a standard deviation below the mean. In this particular problem, that distance is 1.7 because the standard deviation is 1.7. More importantly, we know that 34% of the distribution is between each of these values. The mean and 1 standard deviation below the mean, 1 standard deviation above the mean. 34% of the area under the curve is from 1 standard deviation above the mean to the mean. 1 standard deviation below the mean to the mean, 34%. All right, let's think this through. What does the IQR do for you? The IQR takes these values that has 25% above and below, right? So we've got this in the center, so we have 25% and 25%. So what does the IQR do? It gives us the range of the middle 50%. Well, guys, that has to be bigger than that part right there. No brainer. It can't be otherwise. All right, let's check our answer. It's going to be right. Let's get on to question number 8. All right, another big one. Okay, this one wants us to do z-scores. So babies born weighing 2,500 grams. Called low birth weight, indicates health problems. A certain country, 3424, mean birth weight 1 month early is 2613, so both standard deviation. All right, so find the standardized score relative to all birth in the country. So that's going to be the information that we're going to use right there, the mean of 3424 and the standard deviation 470. So guys, to find this value right here, we're going to need to take the value, which in this case is 2,500, minus the mean, which for all births in the country is 3424, and divide by the standard deviation, which is 470. Now it's going to be negative because our value is less than the mean, and we want to go to two places, so that's going to be negative 1.97. Alright, find the standardized score for the birth weight of 2500 for 1 month early using 2613 as the mean. Well guys, all we need to do really is just go second function entry, and the only thing we need to change here is we need to change the 3424 to 2613. And that's negative 0.24. So negative 0.24. I'm not sure whether you have to put the negative in or not, but probably don't. For which group is a birth weight of 2500 more common? Well, the one that's more common is the z-score that's closer to 0. So the closer to 0 would be the birth weight of 2500 for children born 1 month early. So where do we find that? A birth weight of 20 to 1 month early, so it's going to be B. Alrighty, question number 9 of 15. A researcher collects a sample of 17 measurements which wishes to construct a 95% confidence interval for the mean. What is the T star? All right, gang, we've done these before. These problems usually give students fits. So let's see if we can figure this out. So we know what we got is we've got a distribution that looks like a normal distribution. But in this case, we have a distribution that has degrees of freedom equal to 16. Because again, our sample size over here was 17. So our degrees of freedom, which defines the t distribution that we're using, is just n minus 1. So we're dealing with the t distribution, degrees of freedom 16. Now what we do is we draw two lines. Whatever confidence level we want, that's the percentage of scores between those two lines, those two marks that we're searching for. Next step is think 90% minus 100, or 100 minus 90. How much are we missing? Missing 10%, right? Half of that 10% has to go there, and half of that 10% has to go right there. Now we let our calculator do the work for us. Guys, inverse t. So as I've explained in previous videos, I'm going to focus on this one right here. This number right here will be the negative, and this number right here will be the positive. We only need to report the positive of it. But this is easier because I just have to go 0.05. Degrees of freedom 16. Now if we had a normal distribution, we put in the mean and the standard deviation. T distributions are a function of degrees of freedom. So I'm not sure what we round to. It's right there, it says 3 places. So this will be 1.746. 1.746. And it's going to be right. All right, number 10. Guys, we're finally getting there. Random sample of 15 colleges taken. So we have a mean problem here, mean debt. 19,168, margin of error, 1101. Distribution is normal, complete. So choose the correct interpretation. So what it's wanting us to do right here is it's wanting us to create the interval. And you know, these things are really, really simple to create when you have the margin of error, right? Super, it didn't get much easier than that situation. So you know, if you take your sample mean, you can find your confidence interval just taking plus or minus the margin of error. So I can take 19,168 minus the margin of error to get the left bound, and 19,168 plus the margin of error to get the right bound. All right, just do entry. The only thing I'm going to do is just change that to a plus. So I'm at 18,067 to 20269. Now what I got to do now is I've got to come over here and find the interpretation. So we can say that we're 95% confident that the population mean, that's what I'm trying to estimate, is the population mean, so that has to be the case. And I'm looking at 18,067 up to 20269. Don't you just love when somebody calls you and you're doing something? All right, 20269. All right, cool. B, can we reject a population mean of 19,732? Was 19,732 between the two bounds? It is. So no, we're not going to reject it. So I need to choose C or D based on the interpretation. So 19 is in the interval. So guys, I'm comfortable with D. Check the answer. It's going to be right. All right, number 11. The average income in a certain region was $74,000 per person. Standard deviation 28,000. Right skewed distribution. Suppose we take a random sample of 1,000 residents in the region. Now, is the central limit theorem, remember guys, central limit theorem for these types of problems kicks in for mean problems when we have a sample size of 25 or 30, more than 25 or 30. This book uses 25, most books use 30. So let's accommodate the book and choose that one. So it is large enough because the sample size is bigger than the threshold of 25. The mean is 74,000. And the standard error, now guys remember the standard error is the standard deviation divided by the square root of the sample size. Random sample, so 100. So 2,800 will be the standard error. All right, the probability. What is the probability the sample mean will be more than 2,800 away from the population mean? Now guys, this is a problem that's going to need a picture. So we've got our mean, which is equal to the mean of the sampling distribution in the center. And then we've got these two values that are more than 2,800 away. And guys, 2,800, what's so holy about 2,800? That's our standard error. So really, we're just talking about anything that's greater than that much away or that much away. Everything from this point to this point is less than 2,800 distance away from the mean. Everything from there up to here, up to that point, has distance from the mean less than 2,800. Anything from there on out is bigger than 2,800 away from the mean. Anything from here on down is bigger than 2,800. So what I need is the area in these two tails. So how am I going to do that? Well, I'm going to focus on this tail right here. So I'm going to start out with negative infinity, because again, this goes all the way down to negative infinity. So I'm going to go negative E99 up to what? What do you think, boys and girls? Well, what value is 2,800 below the mean? The mean is 74,000. And if I subtract 2,800, then I get the value that is 1 standard deviation below the mean. I'm just going to let the calculator worry about all that. Okay, so that's the value I want right there. My mean is 74,000. And my standard deviation is 2,800. So that's my area in the left tail. Because of symmetry, I know that the area in the right tail is equal to what I found over here. So I'm just going to multiply that by 2. So the probability is to 4 places, 0.3173. Number 12. According to the data, the mean quantitative score on a standardized test for female college-bound high school seniors is 500. Scores are normal. Population standard deviation 100. A scholarship committee wants to give awards to women who score at the 98th percentile. Now, again, what is percentile? In this situation right here, mean 500, standard deviation 100. We want the score, we know it has to be up here. It has 98% of the distribution below it. Couldn't be way over here, right? This is at the 50th percentile, in the 60th and the 70th. So the 98th percentile has to be a really big score and much higher than the mean. So I'm going to look for, so it says, well, we need a score of at least, and well, at least means more. So relative to the problem, I'm looking for people who have a score of whatever this is or more. Okay? So guys, clearly the first graph is going to be the one I need there. Now, an applicant would need a score of at least to be in the 98th percentile. Guys, I'm going to let my calculator do the calculations here. So inverse norm, area to the left is 0.98, the mean is 500, standard deviation 100. So I'm looking at around to the nearest integer, so I need 705. Check answer. Good deal. All right, gang, just 3 questions left. Statistics instructor randomly selects 4 bags of oranges, each bag labeled 10 pounds. These things are never what they're labeled. There's variation in everything we do, especially any sort of manufacturing task. So the 4 measured out. So I'm going to put this in my calculator. And first thing I want to do is clear out my old numbers and carefully type in these 4 numbers. All right, so 10.5, 10.9, 3 times. The distribution of weights is normal. Find a 95% confidence interval. Well, guys, here, the population standard deviation isn't known. So I know to get the interval, I'm going to have to use a t-interval. The population standard deviation was known to use a z-interval. Otherwise, use a t-interval. I have my data stored in L1, and I want a 95% confidence interval. So I will say, first of all, we get the right interpretation. The first one's just goofy. 95% confident that the sample mean is between. I know the sample mean is between there because I take the sample mean, build margin of error in both directions, and create a confidence interval from the sample mean. Guys, it has to be in there. It was used to create this thing. So A is just goofy. There's no way that could be the case. B, we're 95% confident that the population mean, that's what we're trying to estimate. So that's clearly going to be it. And the left bound was, what are we rounding to here? The nearest, rounded to the nearest thousandths. So we need 10.482. And 11.118. All right. Does the interval capture 10? It doesn't. 10 is below the left bound. So no, it does not capture 10. We would reject, because it's not in our interval, the claim of 10. All right, gang, 2 left. The weights of 4 randomly and independently selected bags of potatoes labeled 20 pounds are found to be these 4 values. First thing I'm going to do is enter my numbers. Now I've only got 4 there, so I can just type over those. This is actually kind of dangerous to do this, to type over the numbers that are there, because I see a lot of students who maybe will have 5 numbers there and they have 4 numbers in their new data set, and they'll forget to eliminate that last piece of that last measurement, and you know, you clearly get it wrong. Okay, what are we doing here? Part A, using a 2-sided alternative hypothesis. You should be able to reject the hypothesis that the population mean is 20 pounds using a significance level of 0.05. Why or why not? The confidence interval is reported here. I'm 95% confident that the population mean is between 20.4 and 22.4. All right, so if their confidence interval is correct, and we have to kind of take them at their word, know that, or recognize that 20 is not in our interval. So we would reject the hypothesis because the interval does not contain the proposed mean. Now what the question is going to have us do is to carry out the official test of hypothesis. So we are doing that not 20, so we need a not equal to alternative hypothesis. So that has to be C. Now, a test statistic, I'm going to let my calculator do this, all right? So I'm going to go stat, the population standard deviation is not known, so we use a t interval. And, guys, what am I doing? I'm losing my mind here. As I said, use a t-test. So the claim is 20. Not equal to. And calculate. All right, so the test statistic to 2 places is 4.49. The p-value to 3 places is 0.021. We can reject a population mean of 20. All right, gang, this is the question we've been looking for, the last one. It looks like it's an easy one. All right, so a researcher collects a sample of 20 measurements, wishes to find a 99% confidence interval. What value of t? Well, we've already done one like this, but you know, let's just go ahead and be consistent and work it out. So guys, same situation here, right? Just scratch sheet of paper, draw a normal distribution. It doesn't have to be pretty. It's a t distribution, degrees of freedom 1 less than the sample size. Draw your 2 lines. The confidence level that we want is 99%. How much is missing? 1%. Half of it here. 0.5%. And 0.5%. All right? So what am I going to do to find this? Inverse t, 0.005, because when I change the percentage into a decimal, I move my decimal place over 2 places. And degrees of freedom, 19. So guys, this is a very, very, very easy problem. With technology. Wouldn't be so easy. What is degrees of freedom? 19. Wouldn't be so easy if we didn't have technology. So our T star would be, we're going to 3 places, so 2.861. If he decides to use a 95% or less, well guys, 95% is less confidence, so our T star is going to be smaller, which will make the margin of error smaller. Uh-oh, we missed one. What did we do here? Oh, I got sloppy. Man, did I get sloppy. If we go 95%, oh wow, this is going to move in. So what is the T star? It's going to get smaller, isn't it? Well, I just pulled a bozo moment. Let's check answers. Correct. Well, sorry about that. I just, I was ready to be done with this, and I got sloppy. So it just shows, even if you know what you're doing, sometimes you can make silly mistakes. Gang, that's all I got. Study hard. Hope you guys do really well on this final exam. Take care.